So consider another example, the differential equation dy dt equals 0.2y minus t. Now we don't know how to solve this. This is not separable, but we want to estimate the value of y at time 10. So we compute the estimates at t equals 10 for delta t equals 1, delta t equals 0.1, delta t equals 0.01, etc., and compute the relative error from estimate to estimate. Suppose we want the relative error to be smaller than 0.9%. What is that estimate? What are we going to go with as our final y of 10? So I can't always just default to the 0.001 step size, because even that small of a step size could still have massive errors depending on how unstable our differential equation is. So here we have, and once again, the way we could compute this if we were doing this by hand just to see how this would work, this is for delta t equals 1. This is delta t equals 1 right here. And the way we would compute these estimates is, again, to build our table and get our dy dt in here. And so at time 0, we have a y value of 10. The dy dt in this case depends on both the y value and the t value. So I take 0.2 times 10 minus t, which is 0, and that gives me 2. So because my time step is 1, remember now the change in y is going to equal the change in time multiplied by the slope at that instant. So because I'm looking at 1 year, multiplying that by 2 elk per 1 year, if that were the case and that's what we were dealing with, then we would get exactly 1 more elk as our change in y. So at time 1, we would estimate 11 elk, and then we would repeat this again, 0.2 times 11, but now minus 1. That would give me 2.2, minus 1 would give me 1.1. So in this case, our rate of change is actually getting smaller. And now I would take 1 year, multiply it by 1.1 elk per 1 year, and clearly in that case, we're just going to get 1.1 elk. I'm sorry, this should have been 2 elk here, back here. Okay, there we go. And so we can repeat this for regardless of what the step size is. But this is telling me that at time 10, right here, my estimate of y is negative 17.876. If I compare that to a delta t of 0.1, and the way you know that is because it took 100 time steps to get to time 10, 0.1, 0.2, 0.3, 0.4, all the way counting up to time 10. And now my new estimate is negative 33.67. So you can see from here to here, that's a big change, right? That's a massive change. Now I know that this one is more accurate, right? So delta t equals 0.1 is more accurate. I don't know how accurate it is, but I know it's more accurate than delta t equals 1, right? It's more accurate than. So instead of coming up with an exact value, which we don't have, we're going to kind of treat this as it's approximately exact. Okay, right? Because it's more exact than the delta t equals 1. So what I'm going to do is I'm going to do my y estimate for a delta t of 1. That's my estimated value at time 10. Minus my y value for a delta t of 0.1. I'm just going to use this subscript here at time 10. You know what? Maybe I should be a little bit more cautious here. Let's do delta t equals 1 at time 10 minus the y value for delta t equals a half. I'm sorry, not half, 0.1 at time 10. And then divided by the more exact of the two values, which is the y value for delta t equals 0.1 at time 10. So that's going to give me y, the delta t at time 10 is negative 17.87 or 88. And I need to multiply this by 100 to get a percentage. Minus negative 33.67 divided by negative 33.67 times 100. So I'm just doing this off to my calculator here. Which comes out to about negative 46.9%. Okay, that's huge, right? That's a huge change in the estimate from one step size to the next. Now, if I compare it to this next decrease in step size, which is delta t equals 0.01, and you can see that now it's requiring 10 times more computations because I cut the step size into tenths, and now my estimate is this value here. I'm going to spare all the notation here, and so I know that my estimate, or the less exact of the two estimates, is the negative 33.67 minus the more exact one, which is negative 35.61, divided by the more exact of the two, multiplied by 100. So now I come up with negative 5.45%. So we're still below, right? These mean that our estimates are underestimates. And we're still improving pretty significantly from delta t equals 0.1 to delta t equals 0.01. That's a pretty still big improvement, that 5.45%. I'm sorry, I don't want to make these appear linked together. So the change in value from delta t equals 0.1 to delta t equals 0.01, we're about 5. This estimate is about 5%. Yes, I'm sorry. So this estimate is about 5.5% under the more exact estimate. So it seems like there's still room for improvement here. We said that we wanted to get that error to be smaller than 0.9%. So we're at 5.45%. We're not quite there yet. Now, one of the things you may notice with using this applet is that if you try to decrease the step size too much for some functions, unless you have a paid version of the software, it may not necessarily produce what you're looking for. So this guy here does not want to, it'll show me some information, but it doesn't want to print the table for me. It says I'm out of computation time. I, at that point, would like to default to another piece of software. So this equation here, I'm actually using a different piece of software. That's this one. You can find many of them on the web. So this one in particular allows you to input your differential equation y prime, but you have to use y and x. Initial time is 0, initial y is 10. Point of approximation, this is what value of time we want it to compute up until. This is the step size, and then if you know the exact solution, you can type it in here. But we just go ahead and calculate, and it gives me an estimated y at time 10 of negative 35 point something. So here we go, right there. Time 10, it's not letting me get up against it, but about negative 35.881. So in this case, if I now look at the change in my estimate, I can see that it has not changed very much, right? It went from here to here. So the more approximate of the two is we want to do estimated, which is negative 35.61, minus the more exact one, which is negative 35.81, divided by negative 35.81. So notice how our exact, quote-unquote exact value keeps changing, because what we're treating to be the more exact value is the one that was computed with the smaller step size. And this comes out to about negative 0.56%. Now, so the change in precision we were only in terms of these two errors, these two values, the error, this value, this negative 35.61, was just under or just over 0.5% smaller than this negative 35.81. Now we wanted to keep estimating until we were certain that our relative error from step size to step size was smaller than 0.9%, and this is smaller than 0.9%. So since the change in precision was less than threshold of 0.9%, we estimate that y of 10, and maybe down here I'll just say that this was for delta t of 0.001, that our estimate is about negative 35.81. And it doesn't matter that it's negative. We're not necessarily dealing with ELK here. This is just a differential equation that we're trying to solve. And now, how close are we to the exact solution? Well, we can't tell from this, right? But we know that by decreasing the step size even more, the relative error is going to get even smaller and smaller. So you kind of have to set your threshold. I chose 0.9% arbitrarily. I didn't want to use 1% because we have all these 0.1s floating around and 0.01, so I just chose 0.9%. Now, it turns out that we can solve this differential equation using a method that we'll later establish. And by the way, the exact solution to this differential equation is negative 35.8358. So check out our approximation here. We're very, very close. So this relative error analysis, by decreasing the step size and comparing adjacent estimates, is actually seems to be a pretty good way for this, at least for this function, a pretty good way for me to hone in on what that exact solution is. There are other better methods than Euler's. There's something called improved Euler's and the Runge-Kutta method. We will take a look at those in the next lesson.